Hi there everybody, and welcome to today's calculus notes. Today we're talking about section 2.5, implicit differentiation. Before we get into the differentiation, let's talk about the difference between an explicit and an implicit function. So an explicit function is a function where y has been explicitly written as a function of x. And you can see there's a couple examples here of explicit functions. So we see y equals negative 2x plus 3. And you can see here y is by itself, and then all the x's and everything else is on the other side. Here's another one, y equals plus or minus the square root of 9 minus x squared. So these have been written explicitly in terms of y in terms of x. For an implicit function, this is a function where y has not been explicitly written as a function of x. So if we look over here at our implicit functions, we can see y plus 2x equals 3. And you can see that the y's and the x's are combined on one side. Okay, so this is another example, x squared plus y squared equals 9, x times y equals 1, and then here you can see x's and y's on the same side. So again, explicit, it's going to be y equals some function of x, and then implicit, the x's and y's can be anywhere. Now, looking at this implicit function, you can always get the explicit function by solving for y. Okay, so that's all you would have to do is solve for y. And it gives us this function here, which then we could find the derivative of. Okay, and then we can just use the rules that we've learned to find our derivative. Okay, so this one will just be negative 2. This case, it's a little bit more difficult to solve for y in this case, right? You'd have to subtract your x squared and then take the square root, giving you plus or minus. So there's actually two explicit functions that are needed to define this implicit function. Now, if we were to find its derivative, we could use the rules, right? Change this to the 1/2 power and then use the chain rule, and we would end up with this derivative right here. So let's take a look at this implicit function, x times y equals 1, and let's go ahead and write it explicitly. Well, we want to get y by itself, so we would just divide both sides by x. And so we get y equals 1 over x. From here, this explicit function, we would know how to find the derivative. So we're going to change this to x to the negative 1. And then to find our derivative, dy over dx, it would be negative 1 times x to the negative 2. And then we would just rewrite that as negative 1 over x squared. Okay, so we have a process by which we can find the derivative of an implicit function by first writing it explicitly and then using our rules to find the derivative. However, let's take a look at this last one. Now we have y cubed plus y squared minus 5y minus x squared equals negative 4. So we could try to solve this explicitly. Okay, we would add our x squared over, and then we would be left with this mess over here. And in order to get y by itself in this case would be extremely difficult. Possible, but very difficult. So we're not actually going to be able to do this because we don't know enough yet. So instead, we're going to try to circumvent the explicit function and go straight over to the derivative, or dy dx. So this is where implicit differentiation comes in. It's going to be used to find derivatives of implicit functions, especially those that are difficult to write explicitly. So especially to find functions like this. Okay, before we can differentiate implicitly, we need to learn what does it mean to differentiate with respect to x. Well, if the variables match, then we're going to do simple differentiation. Okay, so if the variables match, simple differentiation. If the variables don't match, all we have to do is use the chain rule. Let me show you what I mean by that. If we look here, we're finding the derivative with respect to x. Okay, and this sentence here translates into this. So it's d over dx of our function. So in this case, look at the variable x there, and we have the variable x here. It turns out that these match. And when the variables match, we do simple differentiation. So we're just going to use the rules that we know. So we're going to go 2 times 3 is 6, x, and then 2 minus 1 is 1, so we just get 6x. So here we can just use the simple power rule. In our next example, here we have the derivative with respect to x of y cubed. Now we're going to assume that y is some function of x, but notice now that our variables don't match. Okay, so in this case, we're just going to simply use the chain rule when the variables don't match. So we just think of, okay, well, y is some sort of packet, and there's a function in there, but we can take the derivative by going 3 times y squared. Okay, so that's just our power rule. And then we're going to have to multiply by the derivative with respect to x of that y function. And it may sound complicated, but all that is to write dy over dx. So before, we were writing u here, and then u prime out here. Okay, so we can see here's our u prime. Now we're just going to leave it, the variable y, and instead of writing y prime, we're going to write dy over dx. So the derivative of y with respect to x. Okay, so in this case, you have to use the chain rule. Let's look at our next example here. We're looking for the derivative with respect to x of our function x plus 3y. Now here, we can just use the sum and difference rule, and we know that we're going to be finding the derivative of both of these. So here, in the first case, they match. So what's the derivative of x? Well, it's just 1. And then the derivative with respect to x of 3y, okay, we're going to have to use the chain rule. So first, the derivative of 3y is 3. And then what's the derivative of y with respect to x? dy over dx. So you might want to make a note here that sometimes you're just going to use the power rule and the chain rule. Okay. Moving on to our next example. Here we have the derivative with respect to x of x times y squared. So x times y squared. Here we have two functions. Notice one of them, the variables match, and then the other one doesn't match. So in this case, we're actually going to have to use the product rule because we have a product of functions. So it's our first function, x, times the derivative of our second function, y squared, plus our second function, y squared, times the derivative of our first function. Now sometimes I'll just say derivative, but we really mean the derivative with respect to x in both of these cases. So that was the product rule. So let's go ahead and find these derivatives. So the derivative with respect to x of y squared, well, it's going to be 2y dy dx. Okay, because that y didn't match right there. So we get x times 2y dy dx plus, let's see, what's the derivative of x with respect to x? Well, that's just 1, so plus 1 y squared. We use the chain rule here. And overall now we get 2xy dy dx plus y squared. Okay, and this would be our final answer right here. Alright, now that we know how to differentiate with respect to x, let's go ahead and take a look at implicit differentiation. So the very first thing that we want to do is to differentiate both sides of the equation with respect to x. In other words, what we're going to be doing is taking the d over dx of both sides. So just what we did in the last example, we just do this to both sides of the equation. Then the second thing we want to do is to solve for dy over dx. Okay? In other words, we want to get dy over dx by itself. Okay? So in our first example, it says find the derivative of y with respect to x, which is this right here, dy over dx, of these equations. So our first one is x squared plus y squared equals 9. And notice this is implicit because x's and y's are on the same side. So we're just going to find d over dx of both sides. Okay, now we take each side here just like we did in the previous examples, and let's differentiate x squared plus y squared with respect to x. So here the variables match, so we just get 2x. For y squared the variables don't match, so we use our power rule, 2y, and then the chain rule. So the derivative of y with respect to x is just dy dx. In the right side now, the derivative of a constant is 0. So that drops out. So that accomplished our first part, differentiate both sides of the equation with respect to x. The next part is all algebra, solving for dy over dx. So that's what it means to find the derivative. So we really want to focus on this guy right here. We need to get this by itself. So now we just use algebra. So we're going to subtract 2x. Okay, and again, follow the bouncing ball. We're looking for that dy dx. So then to isolate that, we're going to divide by 2y. And then finally here, we are going to simplify this equation on the right-hand side. So negative 2 over 2 is just negative 1. So we get negative x over y. And you can see we've gotten dy dx by itself over here. And then, very interesting now, we have x's and y's on this side. And so when you do implicit differentiation, it's going to be okay to have both variables, x and y, in your answer. Kind of an interesting thing, but don't freak out when you see that. Now, we could write the derivative only in terms of x. To do that, we would have to write this function explicitly, okay, meaning get it into y equals form. So we could, let's just rewrite our function here. So notice we could subtract x squared give us y squared equals 9 minus x squared. Then we could take the square root of both sides. We get y equals plus or minus the square root of 9 minus x squared. So be careful here, just because 9 and x squared are perfect squares doesn't mean that we can take the square root. We would just leave it like this. So then all we would have to do is substitute this expression in for y. So we could write negative x over plus or minus the square root of 9 minus x squared. And because we have a negative divided by our plus or minus, it doesn't really matter. We can change that to positive. So this would be the derivative written in terms of x. But either way, it works. And it's kind of interesting because we see that the derivative, actually, there are two functions that we have here, the positive and the negative. All right, let's move on to letter B. And I want you to try this one by yourself. Okay, go ahead and find the derivative of y in terms of x, and then see if you can't get the derivative only in terms of x. So I'm going to pause the video, come on back in a few seconds when you're done here. All right, welcome back. So you should have taken the derivative of both sides. Here, implicitly, finding the derivative here, have to use the product rule, and then our chain rule here. And then solving for dy dx, we get negative y over x. So there is your derivative. And if you wanted to find this in terms of x only, you would solve this equation explicitly, and then substitute y, and then simplify. All right, let's move on. All right, for letter C, let's go ahead and work this one out together. So you notice the y's and the x's are on the same side. This would be a really tough function to find explicitly, so let's just do implicit differentiation. So find the derivative with respect to x of both sides. Okay. And here we just have the sum and difference, so we're going to find the derivative of each of these terms. Remember, if there's a y, we're going to use the chain rule. So here we get 3y squared dy dx, and then plus 2y dy dx minus 5 dy dx. Now here, this is in terms of x, so the variables do match, so we don't need to use the chain rule. We'll just go minus 2x. And then here, derivative of a constant is 0. Now, in this case, what's different is that we have multiple dy dx's on this side of the equation. Our goal is still to get dy over dx by itself. So to do that, we're going to isolate any term with the dy dx on the left side, and then move every term that doesn't have dy dx to the other side. So here we do want to add 2x. And so we're left with all of this. And equals 2x. So again, this is what we're looking for. We're looking for getting that dy dx by itself. Now in this case, since it's a factor of each of the terms now, we're actually going to factor out the dy dx. Okay, And so we still have 3y squared plus 2y minus 5, and it still equals 2x. Now you can see we're doing a better job here of getting this dy dx isolated. So one last step to finish the job, since this is multiplied, we're actually just going to divide the 3y squared plus 2y minus 5 on both sides. Okay, so now you can see that's going to cancel here and here, and we're going to be left with dy over dx equals 2x over 3y squared plus 2y minus 5. And because we have dy dx by itself isolated over here, this is our final answer. In this case, we're just going to leave our y's in our derivative because we're not going to solve for this explicitly. Alright, let's move on to letter D. Alright, at this point you have all the tools it takes to find this derivative. That's pretty beefy right there. Look, x cubed minus 2x squared y plus 3xy squared equals 38. So I want you to find the derivative with respect to x of this implicit function. Okay, so go ahead and follow kind of the steps that we did here, and notice that you're going to have the product rule happening twice here. So this thing's going to get pretty lengthy here. But go ahead and give this a try on your own. If you get stuck, go ahead and fast forward and take a look at my answer and see if you can't figure out what I did each step of the way. Alright, so be strong and courageous. And good luck, and we'll see you back in a little bit here. Alright, welcome back. So take a second and just look over this work. You can pause the video, and I'm going to walk you through it right now into what I did here. So I took the derivative of both sides. Now the derivative of x cubed is just 3x squared. And then I took out the minus here. And then the derivative of 2x squared y, I had to use the product rule here. So the first function times the derivative of the second, okay, plus the derivative of the first function times the second function. Then plus, now this derivative is also going to need the product rule, so it's our first function times the derivative of the second. Notice the chain rule here, so we had 2y dy dx plus the second function, y squared, times the derivative of the first 3. So there's our 3y squared. From here, we've done all of our differentiating, and now we just want to organize it and simplify it. So I distributed the negative right here. So that gave me these two negatives here. And then here I just multiplied 3 times 2 to get 6 right there. Everything else is the same. Then what I did is I grouped everything with a dy dx on one side of the equation, and then everything that didn't, I moved to the other. Okay, so you can see this term right here got subtracted over here. You can see this term right here got added right here. And then you can see this term right here got subtracted onto the other side of the equal sign. And then my two terms with the dy dx stayed over on the left. Okay. From there, I went ahead and factored out my dy dx. Okay, and you can see this term and this term are right here. And then I isolated dy dx by dividing this to both sides. And there I have my final answer. You should feel very accomplished. This is not an easy task. If you're still confused, keep going back through it until you can figure out exactly how this was accomplished. All right, in our next example, we're asked to determine the slope of the tangent line to the graph of x squared plus 4y squared equals 4 at this point, square root of 2, negative 1 over root 2. So if we're looking for slope, we want to remember that slope is the same thing as the derivative. So this is the same thing as our dy over dx. So it's exactly what we've been finding. And here we have our ellipsis. We want to find the slope at square root of 2. And so the square root of 2 is about right here. It's about 1.4. And so we're trying to find the slope of the equation right here. So we can kind of see where that is. Okay, but we're trying to find the slope of this tangent line right here. Okay, so we need to find dy over dx, which is going to be implicit differentiation. So we get the derivative of both sides. And this one's a little bit easier than the last one because there's no product rule in here. Here we're going to get 2x and then 8y dy dx and then equals 0. So we're going to subtract the 2x now. And then we're going to divide by 8y. Then we're going to simplify. And here is our derivative. Now, what we're looking for is our slope at our point square root of 2, comma, negative 1 over root 2. Now notice in this case, since our derivative has an x and a y, we actually need both the x and the y. And remember, if you weren't given the y, you would just plug x into your original equation and then solve for y, and then you could get your y value right there. So what we need to do is substitute these values into this derivative. So remember, slope is dy over dx. And here's our equation. And we're just going to substitute our point into this equation. So we get negative square root of 2 over 4 times negative 1 over the square root of 2. Okay, so we'll clean this up a little bit here. So this equals negative root 2 over negative 4 over root 2. And we know when you divide by a fraction, it's the same as multiplying by the reciprocal. So we really get negative 2 times root 2 over negative 4. And then negative root 2 times root 2 is negative 2 over negative 4 equals 1/2. So what this is telling me is the slope of this line right here is going to be 1/2. And you can see that it basically looks like it's about 1/2. Alright, so determining the slope of the tangent line, you just find the derivative using implicit differentiation, substitute your point in, and then you have your slope. Alright, so our next example says determine the slope of the tangent line to the graph of 3 times x squared plus y squared equals 100 xy at the point 3, 1. Alright, this one is a little bit tougher again because you can see now we have a function inside of another function. So we have the chain rule happening, but then because of this y, we also have the chain rule happening again inside here. I really want you to give this a try on your own. Okay, so you can go through this and see if you can get the process down. You have all the tools necessary to do this. If you get stuck, you can always fast forward to the answer and try to figure this out. And then if we have any questions, we'll discuss it in class. So go ahead and pause the video, give this one a try, and I'll see you back in a little bit. Alright, so let's talk about what happened here. So we took the derivative of both sides. Then we had to do the chain rule because you can see it's a function here inside of another function. So I did 2 times 3, got my 6. And then here's that inside function. Then to the first power. And then we had to find the derivative of this function right here. On the right hand side, here's what's happening. We had the product rule. So we had our first function, 100x, times the derivative of our second function, dy over dx, plus our second function, 100y, times the derivative of x, which is just 1. So we get that. Next, what I did is I found the derivative of x squared plus y squared. So with respect to x gives me 2x, and then of y squared becomes 2y dy dx. Then I distributed this term to both of these, so you can see 2x times my 6 gives me 12x, and then you can see 2y dy dx times 6 gives me 12y, and here's the dy dx. Okay, and then the x squared plus y squared is still here. Nothing happened to the right side here. Then I wanted to isolate my dy dx's. So here they are, and notice now they're on different sides. So what I had to do is actually subtract it right here, and then what I did is I needed to get everything that wasn't a dy dx to the other side, and so I subtracted this term away here and on the other side. So then I just rewrote it, and so you can see here's my first term with my dy dx, and here's my second, and then here's everything else that doesn't have a dy dx. Then I went ahead and factored out that dy dx. Okay, and this is what I was left with here, the two terms here. Nothing happened to the right side in this case. Then I wanted to get my dy dx by itself, so I divided all of this to both sides. You can see that right here. And then I noticed that 100, 12, 12, and 100 had a common factor of 4. So I just took the 4 out of all of those, and I was left with 25y minus 3x times x squared plus y squared over 3y times x squared plus y squared minus 25x. And that was how I found the derivative. Next, we found the slope here at 3, 1. So the point was up here. And all I did was substitute in for x and for y. So you plug in your x values and your y values. And then you just keep simplifying down. And I ended up with 13/9 as my slope. And if we look at that line, it does look like it's about 13/9. Okay, so it's positive, a little steeper than 1, but not quite 2. And that's how you do this problem. All right, that has been implicit differentiation. Hopefully that made a little bit of sense to you. and I look forward to seeing you all back in class.